So Matt is a MD at Accenture Analytics. So I think really looking forward because it's going to bring some different perspectives. We had some academic talks. We had some talks that are more talking about how machine learning is implemented the dirty way, with code and test. So hopefully, Matt, you can bring some new perspective as well.
Hi everyone, I'm just going to test this microphone that's not too loud. So thanks for the intro, Rahul. So Matthew O'Kane, I work for Accenture in the analytics team. My day job is leading our work in financial services for UK and Ireland. But I've been doing analytics, which is now data science, and we'll soon call it AI, I'm sure, for about 16 or so years after completing a stats degree up in Newcastle. So today I'm going to talk about my little pet subject, and it's not as fancy as deep learning, but for me in my day job of helping clients improve their business outcomes, I find this is one of the most important areas of analytics, and not many people know about prescriptive analytics. So put your hands up if you've heard of prescriptive analytics. 1, 2, 3, yeah, so not many. Traditionally, when we talk about analytics, we talk about these 3 steps, and again, I don't really like them as steps because they're all connected, but the first thing is more about descriptive analytics, so standard statistics, aggregation, looking into the past of what's happened, and then we sort of move up to predictive analytics, so your traditional predictive models, regression, decision trees, random forests, etc., which are there to predict something in the future, or a supervised learning approach. And then when people look at prescriptive, they usually associate that with things like optimization, linear programming, dynamic programming, genetic algorithms, etc. But there are a number of set of prescriptive approaches to problems, and prescriptive analytics is really around helping you make decisions. So the 2 examples you'd normally think of are personalized medicine. The exact treatment I give you as a person influences what happens later on. Hopefully you live rather than die. That's prescriptive analytics. It's an individual treatment to a person. On the business side, different treatments you give to a particular customer influences whether they stick with your brand, whether they stay with you, whether they spend more, whether they complain. So it influences people. Now, the best example I have of this is rewinding far back in time from one of my first jobs after university. I used to work for a bank, so about 15 years ago, I think it is now. I just joined this bank after a couple of years at Rolls-Royce, finished my stats degree, really enjoyed doing things like regression and logistic regression models and things like that. And I arrived at the bank and they said, right, we've got all these different problems we think we can apply prediction to. One of them is debt collection. So in debt collection for this bank, if you miss 2 payments for your loan, we kind of get a bit worried, and we think, is this person going to give us all the money back? But if you then miss the 3rd payment, that's the story's over. You're never going to pay them back. So the debt collection problem was looking at people who missed 2 payments down and saying, is this person going to miss the 3rd payment or not? So I was like, right, okay, let's look at this as a problem. I then spent 3 months building the most perfect logistic regression model known to man. I spent many days looking at different factors, came up with the top 20 factors in my model, put them in, created a report that I think was about that big of everything around us, and then took it back to the collections team. Very excited. I said, look at this model, it's fantastic, and they agreed. They said, the factors going into this model, we can see influence whether someone's more or less likely to roll to that 3rd payment down. And then someone at the back said, that's great, so what do we do with it? And I didn't really think about that. I was like, I'm not really sure. Maybe it's the people who are really high risk, we should definitely call them 10 times. Or is it the people who are in the middle? Are the people at the top definitely going to roll to 3 and they're gone? There's no way we can save them. We should focus our efforts on the 40% guys or the 10% guys. And I got really confused about this. And at the time, I didn't realize around prescriptive analytics, this was a prescriptive problem. What the debt management team wanted us to know is, if I call this person at this particular time, or if I send this letter, what's the change in probability of them rolling to 3? I want to, my business, change the probability. I don't really care about the overall probability. I just want to bring it down. So this is the problem around prescriptive analytics, and it goes by many, many names. And this is the real problem in literature at the moment, where you have to search for uplift modeling, net lift modeling. If you go into the medical area, it's heterogeneous treatment effects and things like that. So there's many, many different words of this. But really, what we're trying to do is, between one or two alternatives, we want to know the change of choosing A versus B. So if we give them the green pill versus the red pill, if we give them the phone call versus just leave them alone for the next week, what's the change in our result? And in my world, in financial services, for banks and insurance companies, there are so many areas you can apply this to. So customer retention is a great example. You know, I don't care if you have a 90% chance of leaving the bank in the next month. I want to know how to stop you to leave. I want to know how to change that 90% down to 10%. So there's many, many areas in my world, but I'm quite sure, you know, we look across a lot of businesses, we look across the medical areas. This application of prescriptive analytics is incredibly important. And very, very similar to deep learning, you go back to, what's that, 1974, and someone's already thought of this. So Rubin, very, very famous around the view around the causal effects of things. And really, when we're looking at this, first of all, we're looking for what's the average causal effect of doing something. So the average effect of giving people drug A versus drug B. And then we want to get down to the individual effects. So what's the individual effect of me doing A versus B? Now, unfortunately, there's a bit of a problem in that in the real world. We can't both give you drug A and then wait to see what happens, and then go back in time and then give you drug B and see what happens. We can only give you one drug. So there's only one version of the world, unless we suddenly enter a mirror universe or something, some physicist solves that. So we can't observe the counter treatments, the treatment that we didn't give. So it's a very, very difficult problem. And how that manifests itself is that when we look at our old data, we don't have the full set in front of us. We only have the treatments and the outcomes that we actually gave to people, to customers, etc. in our data. So there's been a lot of work in this field, really, and I kind of think first of all, the problem now is thinking beyond just binary treatments. So you can actually do many different treatments. You can have many drugs, you can call customers, email them, different channels, different people. So our treatment options increase vastly, so we have to operate around that. And really, there's been a build-up of techniques over time around how to tackle this. So the very, very bottom, you know, we should all know about A/B testing. So test one against the other in a randomized controlled trial. We can observe the average effect of that. And then we can actually maybe observe that in men versus women. So we can try things in an A/B context. We can look at what the likes of Google do with really vast multivariate testing. So, you know, the example of, I think it was Google who tried 40 different shades of blue for one of their buttons and chose the best blue that won the competition. So we can get really crazy in our testing in that way. But we're still looking at average effects. We haven't got down to that one person. So there are a few pieces of literature around how to use this. The first one is just, do we just build one model for every single treatment? Build one model for every single treatment, take one away from each other, and work it out from there. Sometimes that works, but often what you're doing is you're increasing the error rate. So every single time you're adding another model, the errors are interplaying with each other. And there's a little bit of proof coming out that statistically doesn't work, but it's actually, the research probably isn't fully researched out, really. The state of the art at the moment is an area called uplift modeling. And uplift modeling is there purely for two treatments, so a binary treatment problem. And it just looks to try to measure the difference as it adds different variables into the equation. So it may look at the difference between treatment 1 and 2 for males versus females, for old people versus young, and it tries to find where there's a difference, a sensitivity to that treatment. So this is all leading up to the work we said at the top, work with MIT and Accenture. So this came about, I've been looking at this problem for 15 years and scratching my head around it and tried many different techniques, you know, worked in consulting, worked for banks, insurance companies, and always came back to this problem. So 4 years ago, we started a 5-year research agreement with MIT and Accenture. And the idea was we get together with some clients, we get clients' data, we get some bright people at MIT, we get me in the middle, and we try to figure out really thorny problems. So when this came about, the first thing I did was put my hand up and say, this one, let's solve this one. So I was very, very beneficial to work with one of the professors of MIT, Professor David Simchi-Levy, and some of his PhD students. And the interesting angle was David is a supply chain expert, so he's very much around, he understands optimization and is, you know, one of the world leaders in that space. And then we came at from the machine learning side and said, how do we combine this optimization and machine learning problem into one thing? And what popped out at the end, our very, very first algorithm, and I can share the link to the actual research paper if anyone has some weekend time to have a read, what we call conditional treatment selection. And essentially what that tries to do is it's based on, if anyone's heard of things like random forests, gradient booster machines, it's based on a tree structure. The reason why it's based on a tree structure is the fact that we can split by variables and we can find that sensitivity as we keep on splitting, and we can repeat for many, many different trees. So it's a very, very optimized way of looking at this. And the idea is you can try lots of different treatments out with a customer or with a patient, a randomized experiment. You can put it into this model, and the model will tell you how sensitive each customer should be to each treatment. And then you can give the best treatment to each customer and save people or stop people not paying back. So it kind of moves us from that predictive area to that more prescriptive area. And there's a lot of benefits in doing that. So, you know, back before when I was trying this before and I approached this problem, you know, let's say this was marketing and I had a customer there and I said, right, I don't know how to contact or market to this customer. I could try different prices, different channels, give them an incentive. I could change the picture of the email, you know, different times of day. Right, what we're going to do is I'm going to build many models and spend a lot of time building individual pricing models, channel models, everything as I can, combine it all together and see what I can optimize there. Now, it's a lot easier. I can just go to one model. So I can combine all the randomized treatments I have into this one model. So we have one set of data here. I keep the treatment. So it's slightly different from a traditional predictive approach where you have your, you know, essentially your Y and your X as the two data sets, and we add that treatment indicator. And then I can push the target on the side. I can also add different targets. One of the problems you find in business is the fact that unfortunately, there isn't only one key thing you want to actually improve in a business. So in my area, in banking, for example, you know, we want to increase profitability, but we also want to make people happy. We want to keep them around for a long time and stay at the bank. So you have all these competing priorities around retention, around profitability, around customer satisfaction. So we can put all those factors in and start optimizing over them. So we kind of get into two ways of looking at this as a concept. So the very perfect way is the piece on the left here. It's where we can start with our golden source, which is a fully randomized experiment. We run that experiment, there may be 1, 2, 3, 4, X number of decisions, randomize across them, and then we can start our prescriptive approach after that. Often, again, business is a little bit more messy than our nice scientific world. We may not have, on that right-hand side, we may only have some observational data. So they say, you know what, we can't randomize who we call, an email, But actually, previously we emailed some customers and we called them, and we've got some observational data, but it's very, very messy. So the first thing we need to do here is actually take that observational data and try to create almost a perfect experiment, a pseudo experiment as such. There are many, many different techniques. Again, I've very simplified this and said things like propensity score matching, proximity matching, etc. Again, there's loads of literature around how to use them, but they're very, very good in instances. The best example I have is if you look at whether you should smoke or not. Now, we all know that's a bad idea, and the reason how they got to that and could prove that, normally they want to go that left route, and they'd say, let's randomly pick this side of the audience. You guys smoke for 20 years, and then all you guys don't smoke. I'm so sorry for you guys, but I've just split it down the middle. That's what we're going to have to do. It's a randomized experiment. We'll come back in 20 years' time, and we'll see how you're all doing. And then we measured the average number of people. There might be few people here, and maybe more here, and we go, brilliant, we've proven it. You can't really do that. So just the same as business, in life, we have situations where we have this right-hand problem. So what we could do is we can find people who smoke, people who don't smoke, and we can try to find people who look the same. So we might find someone who smokes and someone who doesn't smoke, and they're both the same age, the same background, the same area of the country, and they kind of look almost like twins. If we have enough of them, then we can start to create a rough historic sample of that, okay? So there's a lot of work in literature around that, but that then enables them to start the prescriptive process after that. So with our either actual experiment or pseudo experiment, we can then go through all the different techniques here. And I want you to pick out a couple of interesting ones you can try. In standard packages. So you can try just fitting lots of different models. Sometimes it does actually work. If you fit some really smart deep learning models against every single treatment, you can sometimes get to something that's interesting. You won't really get any insight out of it, but you might get a model that works. In R, there's a really great package you can start off with called the Uplift package. That's come out of, I think it's Professor Leo Gilman in Canada. And there's a set of uplift techniques, mainly based on things like random forests. They are restricted to just binary treatment and binary outcomes, but you can combine them a bit and get around to multiple outcomes and non-binary responses. But if you have any data or you want to try this out with the binary piece, you can just try that package, and they're absolutely fantastic. Then we have the research with MIT on the right. We built some R packages, and we should be releasing those soon. The hope is we can get those into CRAN and get you guys using them as well. And as I said before, you might get this problem where you're trying to now optimize lots of different things at the same time. So CLV, custom lifetime value, or revenue, or utilization, cost, etc. Once you've applied that approach here around uplift or conditional treatment selection, you can then use standard optimization techniques to pick the different levers you want to stretch in that way. So lots of things you can try there initially. Now what we're doing at Accenture, and what's the real difficult thing now. So this works very well on small amounts of data and small sets of treatments and maybe one or two outcomes. But my work with banks, we live in a really messy world. So if you look at that top left-hand piece there, that's a very high level representation of all the things a bank knows about you. It's really scary, by the way. Your transactional data, when you went on online banking, where you live. There's a huge amount of data, thousands and thousands and thousands of pieces of information. Some things like balance are numbers, some things are categories. It's really messy. It's the actual big data issue. And then the bank has lots of different things it could do. Lots of different channels, lots of different techniques, incentives, prices, etc. And then it's stuck in loads of different issues around what to optimize. So the idea is, how can we combine all these different pieces together to work out, for one person here, what we should say, how we should say it to you, and how will that influence how you take up a new product? Will it improve your customer satisfaction? Will it improve your lifetime value? That's the big issue there. What are we doing for time? So we try to develop a set of approaches we can use around really streamlining this as much as possible. And I think I probably described this roughly, but to formalize how you run tests. Can you run tests in a digital channel like Google with its 40 shades of blue, or can you run actual tests with customers in small groups and things like that? How we can enrich that data with all the data that we have around that customer. So again, how can the bank knows a huge amount of information. How do we convert that into a format that we can place into the models? Using the actual algorithms, and again, we continue to progress those with MIT. And then how you can put that back into an optimization framework to prove to everyone that it's actually worked and actually you're producing value and perform that loop. So there are quite some interesting outcomes of doing this, which is interesting. So I've got one example which might be easier to understand if you've used any web form. You've done an insurance application, or you've filled in your name and address details on Amazon, but you'll go through a digital journey, you'll go through an online journey. And what a lot of marketeers and businesses will do, they'll be doing lots of A/B testing of different web pages, the look, the feel, everything. And this is a typical situation here on the left-hand side where we've tried two different versions of this page. You can't see very well there, but the top one has a nice little set of things you could buy, and it has a nice little table and looks very neat. The one at the bottom, the treatment, has every single possible thing we can sell to you. So if you bought, an airline ticket from one of the airlines like Ryanair or someone, and then you click through to the next slide, the next page, and you see every single thing they want to sell you around car hire, baggage, checkup, etc. That's that bottom approach there. And if you do the analysis and you run that as an experiment, what you'll find is that actually conversion rate goes up for the control, but actually you get more revenue at the one at the bottom. So everyone scratches their heads and goes, well, I don't know which one won there, to be honest. So what we can do is we can apply or uplift our prescriptive techniques to, instead of thinking everyone should have control and everyone should have the treatment, we can actually give some of them control, some of them treatment, and we want to find the customers who like tables. Don't know who those customers are, but the customers who like tables and the customers who like to go through and click through every piece and put them in the right bucket. And by doing that, we can then increase both revenue and conversion at the same time. So it's kind of a win-win situation. So we've been applying this, I've talked about banking, my other hat is insurance. And again, we've been applying this across the entire set of things you could do in insurance as well. It's very, very similar things like the web quote journey. So when you want to buy car insurance, we can optimize that. If you call the call center, what product do they try to sell you? Through to managing your claim, reserving, all the way through to your renewals on the right. And finally, just it's a good time. What are we working on now? What we found with these algorithms is that they are incredibly sensitive to the data coming in and how you're applying them. They deteriorate versus a traditional prescriptive machine learning algorithm very, very quickly. So we're always rebuilding them and reweighting them, etc. And it's difficult. So the latest piece our team have come up with is more of what we call a causal forest approach. What we're doing is it's very similar to a standard random forest or any sort of decision tree, a decision forest you've used before, but we're actually developing our rules based on one sample of data, than forgetting about that and actually using another sample of data to assign our sensitivities. It's funny, it's one of those things, again, back to Peter's talk, which seems so obvious in hindsight, and literally the paper for this came out a year ago or something against random forest. So again, using different parts of literature, but trying them in a new aspect into this approach. And now we've developed this, we are now placing deep learning algorithms on the front so we can get more interesting features going into this model. So we haven't quite developed a fully deep learning way of actually solving this, but deep learning on the front followed by this improves the predictive accuracy and the actual sensitivity of the outcome. So that's that. Hope that was a whistle-stop tour. Any questions?
Thanks, Matt.